Okay, now we're going to consider a Lewis structure for a molecule that you've not seen before. It's ethene, and you have not learned how to name these kinds of molecules yet. You'll learn that when you get to organic chemistry at the 200 level. But for now, I'll go ahead and just tell you this is called ethene, C2H4, and I'm going to draw the Lewis structure for it. Again, you might be able to figure out the Lewis structure. Carbon, carbon, double bond, and then 2 hydrogens on each carbon. So we're going to ask ourselves some questions. How many electron domains are around each carbon? And then you can go on and answer the other questions. I think you will have no difficulty answering questions A, B, C, D, and possibly E, but question F may be a little bit of a head scratcher, but don't worry about it. Give it a shot, see if you can figure out what's going on with question F, and I'll explain here in just a moment. So I'll ask you to pause the video and see if you can answer these questions. And when you've answered them, restart the video and we'll go through them. Okay, coming back from pausing the video, we're going to answer these questions. How many electron domains are around each carbon? Carbons are identical, so they have 1, 2, 3. 3 electron domains are around each carbon. How many atomic orbitals must have been used to form each carbon's hybrid orbitals? Well, I had 3 electron domains, so I had to have 3 hybrid orbitals, and therefore I must have used 3 atomic orbitals. Which atomic orbitals were used to form the new hybrid orbitals? Well, if there were 3 of them, it was an S and a P and a P orbital, right? What is the hybridization, therefore, of these carbons? It's sp2. Lowercase s, lowercase p, superscript 2. Which atomic orbital is left over that was not used on each carbon, the orbital that did not hybridize? Well, remember, I have an s and 3 p orbitals. If I only use 2 of them, then there must have been a p orbital left over that was not used in hybridization. So the question then arises, what happened to that leftover p atomic orbital? If it was not used in hybridization to form bonds, what happened to it? And that's where we get down to this section below. The simple answer is that p orbital overlapped with a neighbor p orbital to form the double bond. So let me explain what's going on here, and we can see in this diagram. We're going to talk about this concept called sigma and pi bonds. So we know that atomic orbitals from neighboring atoms, the 2 neighboring carbons, overlap to share a pair of electrons in the overlapping space. That's what a bond is. That overlap is what constitutes a bond. We can describe the bonds based on the type of overlap they engage in, either an end-to-end overlap or an edge-to-edge overlap. So sigma bonds do end-to-end overlap. And there are a few different examples. I can have an s orbital overlapping with an s orbital. They're kind of overlapping end to end. I can have an s orbital that's overlapping with some new hybrid orbital. Hybrid orbitals kind of look a little bit skewed like that, but it's an end-to-end. So for example, if I had an s orbital overlapping with an sp3 hybrid orbital, they can overlap like that. Or I might have a couple of hybrid orbitals overlapping end-to-end. These hybrid orbitals, maybe a couple of sp3 orbitals overlapping end-to-end. And that's called a sigma bond. Now we are showing these bonds as overlapping orbitals, and you can see that these end-to-end overlaps are all called sigma bonds. So here's an sp3 orbital, here's an sp3 orbital, here's an sp3 orbital. Those are on the carbon, right? Carbon used 3 of its atomic orbitals to form sp3 orbitals, and they are now overlapping with their neighbors to form bonds. And what's left over? Here's the p orbital that's left over on that carbon that did not hybridize. Well, if we look at the neighboring carbon, it's doing the same thing. It's got a p orbital left over. But it's forming these end-to-end bonds. And remember, end-to-end bonds are sigma bonds. Sigma is the Greek letter lowercase sigma. Kind of looks like an O with a little swoop at the top. Sigma bonds. In contrast, what happens to these leftover p orbitals is that they can start to do a side-to-side overlap. So let's say there's a p orbital. It's an unhybridized atomic orbital, a p orbital, and it can do a side-to-side or edge-to-edge overlap with another p orbital. And you can see that there's just a little bit of overlapping space there. Sigma bond overlap is stronger, is a better overlap than a pi bond, edge-to-edge overlap. So sigma bonds are more stable than pi bonds. Sigma bonds form first, and then pi bonds can form. So notice that for one p orbital overlapping with another p orbital, I've got 2 overlapping regions. And so I get a top overlapping region and a bottom overlapping region. This is a single pi bond. It means this 2 regions of overlap is 1 pi bond. So we have sigma bonds, end-to-end overlap. And then we have a pi bond that's formed by overlapping the neighboring p orbitals that were not used in the hybridization. Well, let's put this into practice. Let's see if we can actually make sense of this when we look at a molecule. This is a very complex molecule compared to what you've been working on. This is the ethyl cyanoacrylate molecule. It's the organic molecule that is used in superglue, and we are going to label the sigma and pi bonds in this molecule. Again, you would not be expected to be able to draw this Lewis structure, but you will cover this sort of thing when you get to organic chemistry, if you decide to take that class. A couple things that we have to think of first. The first overlap that forms between any 2 atoms in a covalent molecule is a sigma bond. And any additional overlaps that form between those same 2 atoms are pi bonds. So if we go back here and we look at our ethene, we have a double bond here. One of those bonds formed first. It was an end-to-end overlap between two hybrid orbitals, and it is a sigma bond. The second bond that was formed in that double bond was due to the p orbitals that were left behind doing an edge-to-edge overlap, and that gives us our pi bond. So when you have a double bond, one of those little bonds is a sigma bond, the other is a pi bond. And that's what this is saying. The first overlap that forms is a sigma, and any additional overlaps are pi bonds. So I'm going to show you a couple of these. I'm going to assign a couple of the sigma and pi bonds in this molecule, and then I'll let you finish the rest. So let's start over here with this one. Is that a sigma bond or a pi bond? Well, there's only one bond there, right? And we know that the first overlap that forms is always a sigma. So if there's only one there, it has to be a sigma. Same for right here. There's only one bond there, so the first one that forms is always a sigma. So if there's only one, it has to be a sigma. Now let's take a look at this situation. We have a double bond. Well, the first of those overlaps that formed must have been a sigma, and any additional ones must have been pi bonds. All right, so I've given you a model to follow, so I'd like for you to pause the video and go ahead and continue to label the way I have each sigma and pi bond in this molecule. Go ahead and do that now. When you're done, come back and I'll finish this up. All right, I'm assuming you've finished, so let's go ahead and complete this. Every single bond we know must be a sigma bond. Every one that is a single bond must be a sigma overlap. And we know that for every double or triple bond, the first one, it doesn't matter which one we choose, but one of them has to be a sigma bond. And any remaining overlaps must be pi bonds. And here I've got two remaining overlaps. So that's a pi bond, and that's a pi bond. So how many sigma bonds are there in this molecule? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Looks like 15. Let me count that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, it looks like 15 sigma bonds. Okay. How many pi bonds are there? Looks like 1, 2, 3, 4 pi bonds. And I will tell you that this sort of thing is a classic example of an exam question that you might see, to have a molecule to be able to label either the hybridizations or the sigma and pi bonds, and to then report how many there are in the molecule.